We are the flow field of Mare Piccolo di Taranto, and my name is Erica.
And I'm Carlos Martinez.
All right. For the introduction, our research question is how do ocean currents affect particle accumulation and dispersion, and can FTLE flow fields identify potential pollution sources? Our project description is to analyze flow simulation data and create flow fields from the velocity vectors and timestamps, create Lagrangian coherent structures for the particle tracking and finite time FTLE on MATLAB. Our motivation is to identify areas of particle accumulation and dispersion, investigate potential pollutant sources, and to develop and expand methodology.
Now we'll be moving on to the second part of this slides, where's the FTLE results of 1 hour intervals data sets. We came up with this winter velocity field from the data given to us from in-field sensors, where it measures velocity vectors throughout the lake or the basin. We chose the 500 by 500 grid points as our resolution for the data since it provides sufficient data points and throughout the lake, throughout the basin without sacrificing too much of the computational time. To start off, we have the 3 hour winter data set with forward and backward propagation. As you can see, there's some faint FTLE ridges with limited structures. Um, Most activity are closest to the coast and mostly shows where heavy flow speeds are originating from, kind of giving us more of an insight or potential pollutant sources. Now moving on to the winter data set for 6 hours. The the ridges are more defined and they start spreading throughout the whole area, which indicate that attracting LCS pathways, especially in the backwards propagation. Next is the 12 hours. The path is being created to show where heavy flow is prominently traveling to. Strong transport barriers are visible during their forming stages. Um, so just basically transport pathways are emerging and becoming more visible after 12 hours. Now we're moving on to our final data set for the winter of 1 hour intervals with the forward and backward propagations. These are well-developed attracting and repelling structures with a complex ridge network. Ridges correlate to material lines where particles converge, and that would be for the backward propagation, and pollutants are often channeled along the high FTLE ridges. Um, and yeah, now moving on to the summer velocity field, 500 by 500 grid points as well. All of the velocity fields would be 500 by 500 since this is the most optimum computational time and detailed. Again, we're just going to be starting now for 3 hours now with the forward and backward propagation. Similar to winter, there are weak initial ridges present, insight to possible sources of pollution as well. Um, the 6 hours are more defined and denser than winter, shows more active stretching in both forward and backward propagation. 12 hours, very strong FTLE ridges, especially in forward plots, representing dispersion. Very prominent in both plots though. Next is the 24 hours. This one has more higher spatial complexity and intensity of LCS. Uh, we hypothesized that this hence to increase turbulence due to thermal activity and human activity as well, influencing the flow field. And yeah,
So we also analyzed how potential pollutant sources interact with flow patterns using the 24-hour FTLE maps in both summer and winter conditions. Starting off with the wintered forward FTLE, it shows how pollutants may move from their release points, and the flow here is more directional and less mixed compared to summer, which means pollutants tend to stay more localized. And I've outlined on this one and the next ones on the slides the boat launches, the water runoff from the farmland, mostly to the right, the military and naval base activity, and tourism and recreational activities. The next one is the winter backward FTLE, which are the patterns are more structured and less dispersed. allowing us to better identify source regions like areas near industrial discharge points or harbor zones more towards the left side, showing the more red outline, which seem to contribute to a clear traceable accumulation zone, and that steadier flows make it easier to connect sources to downstream impacts. Next one is the summer forward, is we look at where the particles released now might end up. Again, with high dispersion, especially in recreational and nearshore areas, we could see the spread of contaminants quickly through both basins. And then for the summer backward, this shows where particles are most likely to move, at least again near boat launches and farmland runoff zones and tourist areas to contribute to widespread dispersion, especially along the edges on the right side, the rightmost basin, I mean. The chaotic summer conditions would lead to higher mixing, making it more difficult to contain or trace pollutants.
Now we're moving on to the next FTLE results, which is 5 minute intervals instead of the 1 hour intervals of data collection. Again, 500 by 500 grid points. This would be, for these data sets, we do have different z-axes, so there are different levels of basins. For this first one, we will be looking at the bottom winter velocity field. Again, this is for 5 minute data intervals. So this we collected the 15 minutes since we have more available data. Um, we also collected 30 minutes since we also have more available data. And as you can see, it starts out kind of weak at the 15s, and then it starts getting more defined in the 30s, um, where the shorts show accumulation areas, and it's useful to understand local effects or evaluating contaminants associated with these discharges. We this is the next data set for 1 hour, and then 3 hours for 5 minutes for the bottom of the winter data set. Now we're moving on to 6 hours. As you can see, we have a lot more data to work with, and it's becoming to get more cluttered. This is the bottom of the winter temperature map gradient. There's most of it is stable since it's bottom of it. The light doesn't reach down there as much as um on the surface. And as you can see, it's mostly just cool and stable. Now moving on to the surface winter velocity field. This is a different z-axis. Again, just 15 minutes. A lot more activity than the uh, bottom of the basins. Again, 30 minutes, 1 hour, 3 hours, 6 hours. Again, we chose to discontinue after 6 hours since the next data set, next time step was 12 hours and it just didn't was making the charts unreadable. Uh, Now this is the comparison between the 5 minute and 1 hour intervals. The 5 minutes will be on the left side, and then 1 hour intervals will be on the right side. For forward and then backwards, this 5 minutes and 1 hour. The reason we show this is because we say that it's fair to take various time steps and of data collection due to, yes, the 5 minutes is more defined, but it does fall short on collecting data sets for longer periods rather than the 1 hour intervals where it does struggle to initiate, but as soon as it gets more hours in, the structures become more defined. Now this is the average surface winter temperatures. So you can see mostly it's on the farmland side on the eastern basin. Now moving on to the bottom of the summer velocity field, same explanation, same everything 500 by 500 grid points. Again, it starts off with most of the flow just starting off at the shores where we're pointing to potential pollutant sources. Now moving to 30 minutes, 1 hour, 3 hours. Bridges are starting to become more defined, especially in the backwards. We're filling up the middle area in the eastern basin. And then 6 hours. We just continue after 12 hours. due to clutter of the map. Now this is the summer temperature of the bottom of this during summertime. Pretty consistent. Some of these points are lighter color, so they are lower temperature. Um, yeah, that's the bottom of it. Now we're moving on to surface summary of the velocity field. Pretty consistent to where most of the flow is coming from. Usually the channels on the western side of the basin and by the shores. Uh, that was 15 minutes. This is 30 minutes. A lot more rapid. Um, more rapid the structures are created, and then this become more defined after 1 hour, 3 hours, 6 hours. There's some eddies and vortices that are created from this. Comparing the forward FTLE plots between the 1 hour intervals and 5 minute intervals and 1 hour intervals. Again, just to reemphasize that you need both timestamps for each collection data sets to be able to get a full picture and they complement each other. Now this is backwards for 6 hour, 5 minute, for 6 hours, 5 minute, and 1 hour data sets. There's a big eddy right here, which we will discuss in more detail later. Now, this is the average surface summer temperatures, a lot more defined and gradient. There's this full spectrum right here, cooler on the eastern side, and then super hot on the western side. Most of the naval base is over by the western um, basin, and then a lot of high temperature flow coming in from the ocean.
Now on to the conclusions and suggestions. To wrap it up, I would like to start off with the seasonal conditions. As for in the winter, the water flow is steady and we can see clear zones that lead to things like accumulating, and it makes it easier to predict where materials or particles will end up. But in the summer, the system becomes more chaotic with stronger dispersion, mostly due to two factors, which is heat, which affects the water structure, and boating activity, which stirs up the water and adds a lot of movement. When we look at interval variation, or how we often collect data, that also changes that we see. A 1 hour interval helps to capture a larger flow structure and gives us a good overview over longer times. And a 5 minute interval shows smaller and more detailed features like eddies and gives a clear picture of short-term changes. Finally, human activity plays a really big role in influencing the flow. And we have the Italian naval base shown in the top image that brings consistent ship movement and operations. And then there's civilian shipyards and fishing areas shown in the bottom image, which also shows flow patterns, especially during busy summer months, also along with fishing. Altogether, this would tell us both natural seasonal changes and the use of human use of the area shape the flow and the dispersion dynamics in significant ways. So future suggestions, after looking at our conclusions, there are a few important directions we think future research should take. First, it should be really useful to include salinity and density data. These factors affect how water layers form and move, especially in a semi-enclosed system like this. Adding them could help explain more of the flow behavior that we're seeing. Second, collecting multi-year seasonal data that would give us a better idea of whether the patterns we found are consistent over time or just a part of short-term changes. With more years of data, we could see long-term trends more clearly. Another suggestion is to do a more detailed bottom topography mapping, which is the shape of the seafloor has, which the shape of the seafloor has a big impact on how currents move and where materials tend to collect. Having that data would make our models way more accurate. And lastly, we recommend doing more depth level analysis, which most of our current data focuses on the surface, but the water at different depths can behave very differently, and understanding what's happening below the surface could give us a more fuller picture. Overall, these steps could really help us improve future studies and lead to a more complete understanding of the area.
And that's going to conclude our presentation. And thank you so much for listening.
Thank you.